Here are some examples of situations in which one finds volumes of solids of revolution by means of calculus. And we're going to start with an item that matches the first animation that we saw, where we have the region bounded by the line y equals 2/5 x, the line x equals 5, and the x-axis. And we're going to rotate it around the x-axis, as we saw in the video. We often make that little symbol there to indicate what the axis of rotation is. We, of course, get a cone, as we saw in the previous video. And if we were to slice that cone into thin cross-sections perpendicular to the x-axis, they would all be circular disks. And so the areas of those cross-sections would be pi times their radius squared, but their radius is just given by the distance between the x-axis and the graph, so that's 2/5 x. And if we want to slice really thinly and then accumulate all the way from slices near x equals 0 to slices near x equals 5, we would have an integral. And it would be from 0 to 5, pi times that same radius squared. And I'll maybe take a line to nice that slightly. So we have pi integral 0 to 5. This is going to be 4/25 x squared dx. 4/25 can come outside. I've got 4 pi over 25. And if you differentiate the x squared, I get x cubed over 3 from 0 to 5. And it's still our 4/25. Now 5 cubed is 125 over 3. And of course, 0 cubed is 0, so that's not going to give us anything. And we can do some canceling of 25s. And we get something like 20 pi over 3. Now, if you didn't know any calculus, if this were the bad old days, you would simply say the volume was pi over 3 times the radius squared times the height, which is pi over 3 times 2 squared times 5, which is 20 pi over 3. But where is the fun in that? You might want to know where that formula comes from. And you could actually derive it by taking another triangle bounded by x equals h, y equals r over h times x, and the x-axis. And certainly this length will be h, and a very tiny little bit of reflection or calculation will show that that length will be r. And so a rotation of this thing around the x-axis is going to give us a cone, right circular cone of height h and base radius r. And if we can manage to integrate this up successfully, we should be able to derive the formula. So the volume is going to be integral from one end to another. That's now from 0 to h, pi times the radius squared dx. The radius is again r over h times x. The r squared over h squared, that's a constant, and it can come out in front. So I've got r squared pi over h squared integral 0 to h x cubed dx. And that's still the r cubed pi, sorry, r squared pi over h squared. And that was a mistake. This is x squared until I integrate it. Now it's going to be x cubed over 3 from 0 to h. It's going to be r squared h over h squared times h squared over h cubed over 3 minus 0 cubed over 3, which is 0. Cancel some h's, and what have we got? Ooh, I forgot my pi. We've got pi r squared h over 3. Ooh. In general, you can take some continuous function f on closed AB. You can send it around the x-axis, and what you're going to get is sort of a generic solid of revolution. That generic solid of revolution is going to have circular cross-sections, and its volume is going to be integral from to be of the radius squared dx, and the radius in this instance is just f of x. We'll see some other instances later on where the radius will be a little bit trickier to figure out, or there might even be an outer and inner radius. You might be interested in where the formula for the volume of a sphere comes from, and one could take the top half of a circle of radius r, and of course it's easier if you center it at the origin, and rotate it around the x-axis, and see what comes of that. Now, your volume is going to be integral from one end to the other, so from negative r to r, pi times the radius squared, but the radius is square root r squared minus x squared. Now, we can do ourselves a bit of a favor here because there is exactly as much volume between opposite of r and 0 as there is from 0 to r. So although this is not at all a necessary maneuver, it's a convenient maneuver. I'll just, instead of going all the way from opposite of r to r, I'll go from 0 to r and double it. Squaring the square root, of course, gives me just the thing. And now I'm ready to anti-differentiate. So, oops, keep leaving my pi's out. So I have 2 pi, and then we have, that's just a constant, remember, so that's r squared x minus x cubed over 3 from 0 to r. 2 pi, we have r squared times r, which is r cubed, minus r cubed over 3, minus 0, because I'll get a 0 if I plug 0 into either of those terms. And I've got the 2 pi, and 1 r cubed minus a third r cubed is 2/3 r cubed, and 2 times 2 is 4. So I've got 2 pi r cubed over, I've got 4 pi r cubed over 3, which, as my high school calculus book said when it reached this moment, is reassuring. Final example of this video, and we're going to mix it up a little bit by sending this figure around the y-axis. So this is y equals x cubed, the y-axis, and the line y equals 8 for boundaries. And send this thing around the y-axis. I'm going to have a situation where now my circular cross-sections have a different orientation. They're now perpendicular to the y-axis, and what's that going to mean? Well, the volume is still going to be the integral of a bunch of circle areas, so it's still going to be pi times something squared. We're going to be slicing from 0 to 8, so those are going to be our limits of integration. But then what's the radius? Well, the radius is the distance from the y-axis to this point, if I'm asking about the radius of this particular slice. Now, when we were going around the x-axis, our radii were vertical distances. They were y distances that we gave in terms of x. These are, if we rotate around a vertical line, x distances given in terms of y. And so we'll need to say that if y equals x cubed, x is the cube root of y. And so that's going to be the radius. And our integration is going to be dy. Because y is the variable of integration. So this is pi integral 0 to 8. Let's nicen this up a little bit. This is y to the 2/3 dy. And of course, the rational powers are relatively easy to integrate. So I've got pi, let's see, y to the 2/3 plus 1/5. Need a 3/5 in front. This is from 0 to 8. So I have 3 pi over 5 times, let's see, 8 to the 5/3 is 2 to the 5th. That's 32 minus 0 is 32. So I'm going to say that that is 96 pi over 5, and that is our set of examples for today.